Okay, so today we'll start off by doing problems from chapter 10, and then maybe we'll start the lecture in chapter 11. Okay, so let's see how far we get. So this problem says an automobile starter motor has a resistance of 0.05 ohms and is supplied by a 12-volt battery with a 0.01 ohm internal resistance. Yeah. What is the current to the motor? So here's your 12-volt battery. Here's the Okay, so this is the internal resistance of the battery, and generally this is how you draw it. So here's the EMF of the battery, and you draw the internal resistance right next to it, off of the positive terminal. And here's the load. And see, one of the things I want you to notice is, see, the internal resistance is 20% of the load. So this is the total resistance is 0.06, and 1/6 of the power is dissipated in the internal resistance, in the heat. Okay. So if this load was much larger, then the energy loss here would be negligible. Okay. Anyway, so 1/6 of the power is lost there. Anyway, so the problem says, so let's calculate. Okay, what is part A? What is the current in the motor? Okay, so the current in the motor is, here's Ohm's law, voltage divided by the resistance in the circuit. And the resistance in the circuit is this total resistance. Yep. R total, which is V R plus little r. Yeah. So the current in the circuit is 12 volts divided by 0.06 ohms. Okay, so it's, and we'll multiply both by 100. That becomes 1200 divided by 6, which is 200. Okay, so to start your motor, you need a 200 amp current, and you're trying to do that with 12 volts. That's why the motor resistance had to be small. Okay. So anyway, for your washing machines and stuff like that, you're using 20 to 30 amps. So this is 10 times more current than in the washing machines. Then what is the current in the motor? What voltage is applied to it? So here is the motor, and what is the voltage across the motor is the question. Okay. So the voltage across the motor is the current in the motor times the resistance of the motor. Okay, we'll take these two and make that a 5. 5 times 2 is 10. So the EMF of your battery, the maximum voltage a car battery can put out is 12 volts, but the motor is seeing 10 volts. What happened to the other 2 volts? It dropped across this, the internal resistance. Okay, so the terminal voltage was 10 volts. Okay. Then part C asks you what power is supplied to the motor. Power supplied to the motor is, you can use one of three formulas: current in the motor times the resistance of the motor, voltage in the motor times the current in the to the motor, or this. Okay, so we'll use current times the resistance of the motor. Okay, so 200 times that is 10, 10 times that is, so 2000 watts. So the energy supply per second to start your motor is 2000 watts. Okay, so it's about 20 times as powerful as the 100 watt bulb. Okay, so to crank your motor. And then now they say repeat these calculations for when the battery connections are corroded and add 0.09 ohm to the resistance. Okay, so if your battery connections are corroded, you might have seen them because of well, this resistance increases. Well, resistance is added to this. Okay, so you can think of it adding to the internal resistance. So let's draw another diagram. D. So here is the battery, here is the internal resistance, and here is the corrosion, and here is the motor. That's 0.05 ohms. The corrosion adds 0.09 ohms, and this is 0.01 ohms. Okay, now the current drops to voltage divided by the total resistance, which is 12 volts divided by 0.01 plus 0.09 plus 0.05. You see these two add up to 0.1. That's twice the resistance of the motor. Okay, so all the heat energy is, 2/3 of the energy is being dumped here, and only 1/3 of the energy is getting there. So this is 12 divided by 0.15. So now the current is dropped to 80 amps. Okay. And maybe you might have trouble starting your motor. So they want you to calculate all the rest. Okay, so the voltage across the motor would be now I times R, which would be 80 amps times 0.05, which is 4 volts. Okay. Now the motor is seeing 4 volts. The power delivered to the motor is I square R, which is 80 amps squared times 0.05. And this is 4 times 8 is 320 watts. So the power delivered is, instead of 2000 watts, it's 320 watts. Okay. So if your battery terminals are corroded, maybe you want to clean the corrosion first before replacing the battery. Okay, this problem says 1800 watt toaster, 1400 watt speaker, and a 75 watt lamp are plugged to the same outlet in a 15 amp fuse and 120 volt circuit. The three devices are in parallel, one plugged to the same socket. What current is drawn by each device? Which combination will burn the 15 amp fuse? Okay, so even though it's DC, AC voltage will draw this thing as a DC volt. And we'll draw all loads as resistors, okay? And that's how they're behaving. So this is the toaster, this is the speaker, and this is the lamp. Okay. So this is how everything is connected in your house. See, this is a parallel connection. So this is the live wire, and this is the ground. Each device is seeing 120 volts. This is seeing at 120 volts. This is okay. So they all see the same voltage. And with this kind of connection, if this thing is off, if this thing is switched off, that thing can still work. Okay. So all devices work independently of each other. Okay. Now the problem is the following. So here's this wiring. That is, where is this wiring? Behind your wall. Okay. And you don't want that wiring to burn. Okay. So all those wirings have a maximum current they can withstand. So what do you do? How do you fix that problem? You invented the fuse box. Okay, so you have a fuse box and you put a fuse in there. And what is the purpose of the fuse? What is the purpose? What does the fuse do? The fuse will burn before the wire will burn. Okay, that's the purpose of the fuse. So the fuse will burn at a lower current than the wire. So that way your wire will never burn. Okay. All right, so here's the rating of the fuse. It's a 15 amp fuse. Okay, so that's the maximum current you can pass at that. Okay, and of course your wire probably won't burn till 20 or 25 amp current, and so that's why you put a 15 amp fuse. Okay. All right, so what we'll do is the following. And by the way, so if you wanted to calculate the current here, see this guy is seeing 120 volts. So the current here is 120 volts divided by this resistance. The current here is 120 volts divided by this resistance. And the current here is 120 volts divided by that resistance. Okay. So in fact, in lab today, we'll make this circuit. Okay. All right, so what we'll do is we'll calculate the current through each of these guys. We'll calculate the current through the toaster, through the speaker, and the lamp. Well, they haven't given us the resistance, but they have given us their power rating. Okay, and power is V square I square R VI. Okay, yeah, VI. We'll use this formula. So the voltage each device sees is, we know that, 120 volts, so we can calculate the current through that device. Okay. So the current through the toaster is the power of the toaster divided by the voltage, which is 1800 watts, and it is seeing 120 volts. Okay, so that's 1215 amps. Okay, so the toaster can barely run, okay, without tripping the fuse. Can the toaster trip the fuse? Under what conditions will it trip the fuse? If the toaster is on and you get a voltage spike, it'll trip the fuse. Okay. The current in the, what is that? Speaker is 1400 watts divided by 120 volts, and that's 140 divided by 12. 11.67 amps. Okay, so the speaker will not trip the fuse. Okay, so to trip this fuse, you need 15 amp current, but so if the speaker and the lamp are working together, they're drawing only about 12 and 12.3 amps, so they won't trip. So these two guys can work together. This guy has to work by himself. He's already drawing 15 amps. If you turn on the toaster and the lamp to see if your toast is burned, your toast will never happen because the fuse got tripped. Okay? So this guy has to work by himself. Anything else and you'll trip the fuse. All right, so here's a circuit. It's got multiple voltage sources and several resistors. Okay, so do you guys remember Kirchhoff's rules? Anybody? So this is the Kirchhoff's rule. Sum of currents into a junction is equal to sum of currents out of a junction, and then sum of the voltage changes around a closed loop add up to 0. Okay, so we'll use this rule because we have a closed loop to find the current through this circuit. Okay. Now, which way is the current flowing? Okay, so this battery would drive a current like that. This battery would drive a current like this. Okay, so but since this is a more powerful battery, you'll have a net current in this direction. Okay, but to be contrary, what we'll do is we're solving for the current in the circuit. It's an unknown, so we'll label it I. Okay, I is your X, your unknown. Now we've labeled the direction of the current to be that. Okay, we obviously know it's wrong because I've already told you the current is going to be flowing in this direction. Okay, now if you set up the equations assuming this direction as the current, and the current will come out to be, let's say, minus 5 amps. What does the minus tell you? The negative sign tells you. Yeah, the current in the real circuit is flowing in the opposite direction. Okay, that's what it's telling you. Do you guys know what this circuit is? Okay, what this is a battery that has run low, and that battery is being charged. Okay, so this is your phone dead, and you're charging your phone. Okay, so you do this every day. Yep. All right, so now we've said a couple of things about it. So now we'll use this equation. By the way, so this is the change in voltage across each element. Okay, and we're going to go around the circuit. How many elements are there? 1, 2, 3, 4, 5, 6, 7. So that equation will have 7 terms. Okay. Where do you want to start? You can start anywhere you want, and you can go any direction you want. You can either go clockwise or counterclockwise. It won't matter. Okay. So let's start here, and we'll go clockwise. Okay. So when you go across this element, it's you're going from low to high voltage, so the change in voltage is positive 12 volts. Yep. Then you're going across this element. Current flows from a high voltage to low voltage. So when you go across this, the change in voltage is negative IR1. What is the next term? Negative IR2. The next term?
Minus IR3.
Okay, and IR3. You've run out of your turn. Okay, somebody else. What is the next term? Yep.
Would be plus IR4, I guess? Or plus IR4?
You're going to ignore the battery?
So it'd just be V2.
Okay. All right, let's see. You're going from a high voltage to low voltage. So it'll be minus 24. Okay. And then what's the next term? Actually, I'm going to do the following. I want to illustrate something, so I'm going to change it. I'll write this as plus V1, and this says minus V2. All right, what is the next term? So you're going like that. Current flows from high to low, so it's minus IR4. The next term, minus IR5. And what should all these add up to? 0. All right, so by the way, let me remind you of some. So here is a simple circuit. In this simple circuit, V is I times R. Okay, so let's do this. So now what we'll do is I'm going to bring all the IRs to the right, and so this is V1 minus V2 equal to I times R1 plus R2 R5. So this circuit is behaving just like that. The voltage is the difference in the two voltages. Okay, because they're working in the opposite direction. Okay, so these guys are acting like a single battery whose voltage is the difference in the voltage. Okay, and the resistances, since the resistances are connected in series, the total resistance is just the sum of the resistors. Okay. It so happens that V2 is greater than V1, and so current works out to be negative. Now, currents are not negative, it's just that we chose the wrong direction for the current, that's all. Okay. So that's what's going on. So next time you see in a single loop, if you see batteries that are in the opposite direction, the net voltage is just the difference, and if they're in the same direction, you just add up the voltages. Okay. All right, so, well, when it's like this, okay. Again, what is this circuit? This battery is charging this battery, okay. All right, so we have this is minus 12 volts equal to, so I is equal to minus 12 volts divided by the sum of the resistors, and the sum of the resistors is 10 plus 10, 20, 30, 50, 60 kilo ohms. 60 kilo is 10 to the 3 ohms. Okay. And so 12 goes into that 5 times negative 0.2 into 10 to the minus 3 amps. Okay. So the negative sign just tells you that the current really is flowing in the opposite direction. And this is 0.2 milliamps. Okay, so a milliamp is a thousandth of an amp, and in the lab today we'll be measuring currents that are milliamps. Okay. Yep.
If we would have went the other direction, we would have gotten a positive answer instead.
That's right. So had we chosen this direction as for the current, you would have gotten a positive answer. You would have gotten positive 0.2 milliamps. And I deliberately chose the wrong direction to make sure you understand what a negative current means. All right, so if the batteries are like this, you can add or subtract the net voltage in the circuit. When the batteries are like this, you can't add or subtract, okay, the voltages. Now these are, you got to treat them as independent loops. Even if the battery was here, you couldn't add or subtract the voltages, okay. So now we want to solve this circuit, okay. So what does solving the circuit mean?
Finding the
Currents or the unknowns, okay. So generally it's the current. So in this case they didn't give you one of the voltages, okay. So these are the three unknowns, and we'll solve those three unknowns, okay. We'll find those three unknowns. You're solving for x, y, z, so to speak, okay. You have three unknowns. How many equations will you need? 3 equations, okay. So we'll use Kirchhoff's rules. N equal to which one is the easiest to apply? The current rule is the easiest to apply, okay. And what this is saying is current flowing into a junction is equal to current flowing out of the junction. So this is a junction, okay. And so what is flowing in? I1 is flowing in, I1 and I2 are flowing in, and I3 is flowing out. Okay, so I1 plus I2 is equal to I3. And I1 is given 2 plus I2 equal to I3. Okay, so there's equation 1. And we need 2 more equations, okay. And what we're going to do is we're going to apply this to a loop. How many loops are there in this circuit? 3. 1, 2, 3. Okay? And you can pick any 2 of those 3. Okay? So what I'll do is I'll pick this as loop 1 and I'll pick this as loop 2, and we'll go in the opposite direction just for giggles. Loop 1, loop 2. Okay? So loop 1. And we're going to apply this rule, okay. Now, before we apply the rule, let's count the number of elements in this loop. How many elements are there? 1, 2, 3. So there will be 3 terms on that thing, okay. And we will start here, okay, go around there. What is the first term? Hello there, you in the last, yeah, go ahead. No. Mm-hmm. So we're going to start here. The first element we're going to go across is that guy. And so that'll be plus V1, okay? And then we're going with the current. It's minus I1 R1. And then we're going against the current. Against the current is voltage flows from high to low, so you're going against the current. That's plus I2 R2. you're going uphill, I2, R2, and that's equal to 0. All right, so V1, I1 is 2 amps, 2 R1, R1 is 12, plus R2 is 6 ohms, and I2. And notice I'm not writing units because it just gets messy. So it's V1 plus 6I2 is equal to 24. So here's your second equation. All right, loop L3. For this loop, again, it doesn't matter where you start, and we are going to go counterclockwise. So let's start over here. And who wants to do this? Rain? Go ahead. Start here. This is the first term we're going to go across. You're going from high voltage to low voltage, minus 21 volts. Then you're going against the current, so you're climbing uphill. So it'll be plus I2 R2 plus I2 R2. And then this current is I3, so you're going against the current, plus I3 R3. And what does all this add up to? 0. All right, so 21, so let's put in the numbers. I2, R2 is 6, 6 I2 plus 5 I3 equal to 21. There's the third equation. All right, again, so now what we have done is, what was the goal of this circuit? To solve all the unknowns. For all the unknowns, you had 3 unknowns. And using Mr. Kirchhoff's suggestions, rules, we've set up the equation. Okay? Now we've reduced it to a mathematical problem. Okay? So now we can solve for this. Okay, so what we can do is, we've talked about this before. How do you solve these guys? 3 equations and 3 unknowns. What you have to do is reduce it to 2 equations and 2 unknowns, and then 1 equation and 1 unknown. Okay? That's one way of doing it, unless you want to use determinants and so on. So this is the process we'll employ. And notice here's what you could do. See, if you take this information for I3 and put it in here, then this will become an equation in only I2. And you can solve for I2. Okay? So we'll take information from 1 and put it in 3. Okay. So 6I2 plus 5I3. I3 is 2 plus I2. And that's equal to 21. Okay, so using those, by doing this, now we got an equation, 1 equation and 1 unknown, and we can solve for this. Okay, so this is 6 plus 5 is 11. I2 equal to, this is 10. 21 minus 10 is 11. So I2 is 1 amp. I2 is 1 amp, so this equation tells us I3 is 3 amps. And then what is the last unknown? V1. So we'll put this, I2 was 1 amp, so this would be 6 24 minus 6 would be 18. V1 will be 18 volts. Okay. All right, so we've solved for the three unknowns. Okay, in our answers, the currents came out both positive. What does that mean? In the real circuit, the currents will be flowing in that direction. Okay. Had any of those come out to be negative, for instance, if I2 had come out negative in the real circuit, in the actual circuit, the current would be flowing in that direction. Okay. All right. So on the exam, you will have a question like that, so make sure you understand that. And in lab, we will set up a circuit like this, not this week, but next week. But there in lab, will give you both the voltages, and you will have to calculate the three currents, and then measure and check and see if your calculations are right. Okay? All right, so now we'll do a little more complicated circuit. Okay. Again, solving the circuit would mean that finding all the unknown currents and stuff like that. So they're asking you to find two voltages and one resistor. Okay? And so they give you all the necessary stuff. Okay? So this looks fairly complicated, but let's see. Okay, I'll point out some simplifications. We want to solve for V1. Where is V1? There is V1. Okay. You know this current, you know that, you know this current, you know this resistor. Okay. So to solve for V1, all you have to do is apply Kirchhoff's rule to this loop. We'll apply the Kirchhoff's rule to this loop, and you should be able to solve for V1. Okay. So, okay. Now, how many elements are there in this loop? How much? There are 4 elements. 1, 2, 3, 4. So there will be 4 terms, okay? And what we'll do is we'll go around the loop starting here, we'll go around like that, okay? So it's plus V1, and then we're going with the current, so minus I1 R1. And then we're going with the current, minus I3 R3. And again, we're going with the current, minus I2 R2. And what should this add up to? 0. So V1 is equal to I1 R1 plus I2 R2 plus I3 R3. I1 is 4 times 6 plus I2 R2 is 3 times 4 plus I3 R3 is 1 times 6. Okay, and so that's 24, 12, 36, 42 volts. What's the next one we want to solve for? V2. Where's V2? Here's V2. Okay, to solve for V2, we could use this loop or this loop. It doesn't matter. Okay, so let's use this loop. We'll call it L2, and that's the direction in which we're going to go. Okay, Tatiana, we will start here and go like that. So what you have to do is figure out the currents. Okay, so in each arm, in this arm, this is the current flowing. Okay, I4 is flowing. So we're going to start here, and I4 is flowing like that. So
minus I4R
very good.
and minus I2R2. Oh no, plus.
Very good. So
And then minus V2.
minus V2, very good. Okay, so all you do is, okay, so what you have to remember is current flows downhill, so the voltage change is negative. When you're going against the current, you're going uphill, so voltage change is positive. When you're going across this battery, you're going from positive to negative, so that the voltage change is negative. Okay. All right, so V2 is what you're trying to solve for. V2 is I2R2 minus I4R4. I2R2 is 3 times 4 minus 1 times, what is R4? Oh, R4 was the other unknown, so I guess I chose the wrong loop. I should have used this loop. But anyway, we'll figure it out. So minus R4. So V2 was that. V2 is 12 minus R4. Okay, so this has two unknowns. Okay. All right, so now we'll use another loop, this loop, L3, and go around like that. So loop L3. Okay, who wants to attempt this? Min? Mm-hmm. All right, we'll start here. We're going counterclockwise. We're starting here. So this is your first element. Minus I3R3, you're going with the current. And then you're going from high to low, minus V2. And then, okay, this one. I'm having trouble with this one. Who can help me? Hello? Mm-hmm.
Plus I5R5.
I'm sorry?
Plus I5R5.
Very good. Plus I5R5. All right, so this is equal to V2 is equal to I5R5 minus I3R3. I5R5 is 3 times 4, 12. And I3R3 is 1 times 6, minus 6. So V2 is 6 volts. And then now that we have V2, we can put that in here. So R4 will be 6 ohms. All right. So there you go. You just use those two simple rules, the current rule and the voltage rule, to get as many equations as you want to solve for the unknowns. Okay. All right. So how many unknowns do we have? 1, 2, 3, 4, 5. Okay, so you would need 5 equations. Okay. Let's see, they give us this, I1 is unknown, I2 is unknown, right, all the currents are unknown. Okay, so all right, I'll set up the equations. It's a little messy, so maybe, okay, let's see. We'll see. So what are we using? So the current rule is always easy to use. Okay, so we'll use the current rule for this junction and for this junction. Okay, if you apply it for this junction, if you apply the current rule to the opposite junction, you'll get the same, the junction to the other end of the arm, you'll get the same equation. So we'll use this junction and this junction. In this junction, I1 and I3 are flowing in and I2 is flowing out. So I1 plus I3 equal to I2. So there is equation 1. Applied to this junction. Okay, help me out with this junction. What is flowing in? I4. What is flowing out? I3 and I5 is flowing. Okay, so you have your two equations there. Okay, now you need how many more equations? 3 more equations. How many loops are there in this circuit? 1, 2, 3, 4, 5, 6. Okay, and all you need is 3 equations. So we'll keep it simple. Loop 1, loop 2, loop 3. Okay, loop 1. I'm going to start here. Plus V1, V1 minus I1 R1 minus I2 R2 equal to 0. V1 is 12 volts, 12 equal to 4 I1 minus plus 3 I2. Okay, and then loop 2 gives you, we'll start off here, so plus I1 R1, I1 R1 minus V2 and then minus I3 R3. Okay, so loop 2 gives you, I'll bring V2 on that side. V2 is 5 volts, so V2 equal to I1 R1 minus I3 R3. V2 is 5 volts, I1 R1 is 4 I1. R3 is 2 ohms. There's equation 4. And then the last loop. Okay, so we'll start here. We'll go across this, that's plus 5 volts, plus V2, and then we are going with the current minus I4 R4. equal to 0. So V2 was 5 volts and R4 is 2 ohms. Okay. 5 volts equal to 2I4. So here was the fifth equation, and this gives us I4. So I4, again, right, what I'm going to do is okay, so there are the 5 equations. From here, you can solve for I4. Okay, and anyway, go in a series. So this is I1, I2, I3. Okay, so and then once you solve for I4, these two, and that is 3 unknowns and 3 equations. You can solve for I1, I2, I3, and then put that in here. I4, you know, I3, you know, and you can solve for I5. Okay? All right, so we saw how to set up equations. Okay. Now we'll do RC circuits. Okay, this one says heart pacemaker fires 72 times a minute. Okay, so the heart pacemaker is firing time, how 60 seconds divided by 72 times. So it fires once every 0.83 seconds. All right. Each time a 25 nanofarad capacitor is charged by a battery in series with a resistor to 6.632 times its full voltage, what is the value of the resistance? Okay, so you've seen that this circuit is like so. This is okay, so here's one form of the circuit. So this is the heart. What happens is this switch closes and the capacitor gets charged, And then once it's charged, so in this problem they say once it's charged to 63% its full charge, you open the circuit and fire it and get the heartbeat started. Okay, so you're discharging, you're passing a current through the appropriate location in the heart to get it started. Okay, so what we're trying to find is this resistor, the charging resistor. Okay, so for instance, in your camera circuit, in your flash camera circuit, when your camera is blinking orange, the capacitor is being charged, and we are finding this resistor. So the larger this resistor, the longer it takes to charge. Okay, and then you discharge it through here. So this resistor determines the charging time, and so since they tell you it's firing every 80.83 seconds, this is taking 0.38 seconds. Okay, so this is the part of the circuit where, okay, and the charge, how does the charge on this thing build up? So go check your notes. QT, the maximum charge, here's how you remember the maximum charge. So for a capacitor, capacitance and that are related like that, the maximum charge is C times V. C times V, 1 minus e to the power of minus t by tau. That's, tau is the time constant, RC. RC. This is the resistance of the heart. We're not worried about that part of the circuit. We're only worrying about this part of the circuit. All right, so what do they say? So they say so when at t equal to infinity, this term would be 0. That would be the full charge of the capacitor. Okay? So they're telling you at this time, when it fires, it has 0.632 times its full voltage or full charge. Okay? Full voltage and full charge are related. Okay? So at Q equal to 0.83 seconds, it's got 0.632 times the full charge. C is the capacitance, V is the voltage of the battery. Okay. So 0.632 CV equal to CV times 1 minus e to the power of minus t. T is minus, oops. Okay, so you see everything is unknown. Everything cancels except for tau. Once we find tau, we know the time constant and we know the capacitance, so we can calculate the value of this resistance. Okay, so we'll calculate tau. Oh, I'm sorry, this is 0.83 seconds. take the log of both sides, natural log. As you can see, I'm dyslexic. So the time constant is so the capacitor was firing at one time constant essentially. Okay. All right, so tau is RC, R is tau over C. 0.83 seconds divided by the capacitor was 25 nanofarads. Okay, so this will be 10 to the 9 seconds over farads is ohms. 0.83 divided by 25. Okay, so 33 mega ohms. Okay. So what we found was, remember, the larger this resistance, the slower this thing charges. Okay, so this was 33 mega ohms, and it would take about 0.38 seconds to charge to 63%, and then you fire it. Okay. Now, when you go for a run, what has to happen? Fire more frequently. So you have to charge it faster, meaning you have to reduce this value of this resistance. Okay, so you have to have some mechanism. So let's say when you're going for a run, you're breathing faster. So you got to make some chest measurement and reduce the value of this resistance. Okay, or somehow figure out that you're running or you need more oxygen faster, and then tie that to reducing that. Okay, so that will be a whatever that's called, a variable pacemaker or whatever. And then you can charge people more money and become richer. Yep. A 500 ohm resistor, an uncharged 1.5 microfarad capacitor, and a 6.16 volt EMF, that's a pretty odd number, are connected in series. What is the initial current? Okay. So what they're asking you is the following. So here's a switch. When you first close the switch, what is the current? Okay, so what So the current is the current in the circuit is given by the initial current minus E tau. Okay. So at t equal to 0, this is 1. So that's the initial current. And the initial current is such that the way to remember this is as if this capacitor is not even there. The initial current is just V over R. So that's the expression, V over R, e to the power of. And again, tau is this, what is the time constant? Tau, the time constant, is related to RC. Like that. So in our problem, it's I at 0 is V over R. Okay, so it's 0.012 amps, 23 amps, and this is equal to 12.3 into 10 to the minus 3 amps. And what is this? This is milli. So 12.3 milliamps. Okay. You will measure currents like this in lab today. You'll measure milliamp currents. What is the time constant? Time constant. So that's the time over which things change in the circuit. And this is equal to 500 times 1.5 into. Okay, and ohms times farads is seconds. So this is 750 into 10 minus 6 seconds. So 750 microseconds. So the time constant is, or 0.75 milliseconds. Okay. So things change over milliseconds. What is the current after one time constant? Okay. So what they're saying is put this equal to tau, and this will become e to the power minus 1. Okay. So the current at one time constant is, this is the maximum current, which is the initial current, e to the power of minus tau over tau. So after one time constant, okay, so it's 37% of the initial current. Okay, the current, again, the current is exponentially decreasing. Okay, and this will be the, so it's 37% of the initial current. And then what is it? What is the voltage on the capacitor after one time constant? The voltage on the capacitor. So QT is given by CV1 minus voltage on the capacitor is QT over C C that's the voltage of the battery, 1 minus e to the power of minus t over tau. Okay. And again, we'll put this to be one time constant, so this will become 1 over e. So this is V times 1 minus 1 over e. And this was 6.16 volts. Okay. That was the voltage of the battery. So the voltage across the capacitor is 6.16 volts times 1 minus 1 over e. Okay, so 3.9 volts. All right, so that finishes the problem.